please take it away. Yeah.
All right. Thank you so much to the organizers for a terrific conference, and to all the speakers, and for all the people who continue the discussion on Slack that allows people in different time zones and with different obligations to follow along to discussions that would normally take place in one corner of the coffee break. It's really great to be able to follow along this way. So it's a pleasure to introduce Congkao Wen from Queen Mary, and he'll tell us about new exact results and modular invariance of integrating correlators and n=4 surveying nulls. So take it away, Congkao. I'll let you know when you have 5 minutes left.
All right, thank you. So first, let me thank the organizers for putting together this wonderful conference and inviting me to speak here. So I will talk about the exact results and the modular invariance or integrate correlation functions in n=4 superYAG. So the talk will be mostly based on these 2 papers I wrote with Daniel Doligoni and Michael Green. In various places, I will also mention early work that was done with Shai Chester, Michael Green, Sylvia Pufu, and Yifan Wan. So the object we will study in this talk is a 4-point correlation function in n=4 superYAG with SU and gauge group. So this is a correlation function of 4 superconformal primary operator. I call O2 here. Sometimes it's also called the O20 prime. So this is the build out of the 2 scalars of the theory. And to get rid of the asymmetry index, I introduced this null vector I call Y here. So this is a BPS operator, and it's famously known that the 2 and the 3-point function are protected. So the first non-trivial case is a 4-point function, which is what we are going to study. It is convenient to write this as a free part, namely the part you can compute from free theory, and a remaining one. And the remaining part can be further decomposed, say, into 2 pieces. And I write it as, say, I4 and the Tn, where the P factor, I4, is completely fixed by the symmetry. It contains all the information about this null vector Y, or said in another way, it contains all the information about asymmetry. And this unique function is our focus. Okay, so this is a function of the cross ratio, and it's also a function of the coupling. Things I will be interested in non-perturbative effects. So I will use the complexified coupling. I think sometimes I will also call it as a tau1 plus I tau2, where tau1 basically is the angle and the tau2 is the 1 over g m square. And of course, it also depends on the rank of the gauge group. All right, what is known about this correlator? Well, it is in perturbation theory. This was computed up to 3 loops. As for the integrand, in the planar limit, the integrand was constructed up to 10 loops. And an interesting fact is that the non-planar contribution only starts to end at the 4 loops, and the integrand was also constructed. At the strong coupling, one can compute this correlator using ADS-LT, even in early days of ADS-LT duality. And more recently, there has been a lot of interesting generalizations by including the KK modes, considering loop collections or string collections. The non-perturbative instanton effects were studied in the semi-classical limit. All right. As my title suggested, so we are really interested in this SO2Z modular invariance of this correlator, since SO2Z symmetry relates the correlation function at the weak and the strong coupling. So we want to compute this correlate at the finite coupling. Well, computing a non-trivial 4-point correlation function at the finite coupling in general is very difficult. So instead, we will consider a similar but yet a highly non-trivial object we call the integrated correlator. So the definition is very simple. So you take the correlator, well, say you integrate it over the space-time. Here now it's the closed ratio with a certain measure. And with suitable choice of the measure, which I will describe shortly, this integrated correlator can be computed exactly. At the end of the talk, well, towards the end of the talk, I will also discuss one may reconstruct the unintegrated correlator, at least for the first few orders in the large rank expansion. So there are two integrated correlators that have been studied. I will call just number one and number two. The measure, for the first one, the measure takes this rather simple form. And the second one, well, has the same measure, but insert yet another function I call D111 here. So this is just the D function or the contact Venn diagram. Or if we want, this is just a one loop box integral in 4 dimensions. All right. So before I present, say, our result, let me just comment the simplicity of this integrated correlator. Let me just focus on the first one. So I mentioned that in the perturbation, the integrated correlator was computed up to 3 loops. In fact, at 1 and 2 loops, the correlator is simply given by so-called ladder diagram. And the ladder diagram was famously known, can be computed to any loop order. So L is the number of loop. It's given by this, say, polylogarithms. It turns out the integrate ladder diagram, namely use the measure I just said on the previous page, was also known to any loop order. And then for that, it's just given by this simple Riemann zeta. Now at the 3 loops, the correlator takes much more complicated expression, way more than just ladder diagram. It contains so-called multi-polylogarithms and so on. But we found that if we take that really complicated expression and integrate over this measure, everything collapses, and you just got a zeta 7 with this rational coefficient. But let me emphasize again. So we really want to compute the correlator exactly, not the order by order in perturbation. So this was made possible by realizing a relation between this integrated correlator and the partition function of N2 star super Yamils on S4. And the relation is given here. So N2 star super Yamils is basically, say, N4 super Yamils deformed by some Marston. And the statement is that the integrated correlator is given by, say, you take the partition function and take 4 derivatives with respect to mass or respect to the coupling, and set the mass to 0, go back to N4 super Yamils. So roughly speaking, when you take the derivative, you bring down integrate the operators from the action. So that's how the integrated correlator is related to this 4 derivative acting on the partition function. This relation is useful, of course, because the partition function of N2 star super Yamils on S4 is famously known, can be computed using supersymmetrical localization. So I won't go into any detail here, just to say, instead of a past integral, so this partition function is given by a finite dimensional, n-dimensional integral, and that receive contribution from perturbation as well as from a non-perturbative effect with instant dawn theta on, say, south, well, instant dawn, anti-instant dawn theta on the south and north pole of the S4. In my talk, so I will actually mostly focus on the first integrated correlator. At the end, towards the end, I will briefly comment on the second integrated correlator. So, well, without going into any detail, just to say that we analyze this localization formula very carefully, especially the Nixoff partition function. by studying a lot of examples, we observed some patterns that allowed us to conjecture an exact expression for the first integrate correlator for arbitrary n and arbitrary coupling. The expression takes the following form. We write it as summing over two-dimensional lattice. So P and Q are integers, and all the coupling dependence appears in this particular way. So in some sense, all the non-trivial information contained in this rational function, which I call B and T here. So B and T takes this form, and the numerator I call Qn is a degree 2n-1 polynomial. Well, its explicit form maybe not so important, but anyway, so say for SU2, it's given here, SU3, it takes this form. You may notice it's a symmetric polynomial. So let me make some quick remarks. One is that this rational function has this so-called inversion invariance, namely it's invariant if we take a t equal to 1 over t. That's associated with this symmetry property of this polynomial Q I just mentioned. It also obeys several interesting integral identity. One of them is that if we integrate it over a measure like 1 over square root of t, it vanishes. This property, I mention it because it's important to do a Poisson summation. And Poisson summation is one way to read off explicitly the K-Stone contribution from the formula. So the statement is that a K-Stone term can be obtained from the formula by doing a Poisson summation on P, and the internal number K is basically P hat times Q, where P hat is an integer replacing P when you do the Poisson sum over P. Okay. Another important property is that this is a manifestly SL to the invariant. That's simply because how the complex Phi coupling appears in this particular way. And if we sum over integer, it's easier to show this is a SL to the invariant. Another property is that one may re-express the result in terms of a infinity sum of a non-holomorphic Einstein series with some coefficient, which I don't show here. So, well, this can be obtained by simply taking this rational function and expand around the t equal to 0, and you integrate it order by order. Since non-holomorphic Einstein series will appear again, so let me just remind you, it's also given by a lattice sum for any, well, for complex Phi S as far as the sum is convergent. So one can do a Fourier decomposition for the non-holomorphic Einstein series, where the zero mode is basically the perturbative term, and the non-zero mode are the instantons. Okay. Another important property of this rational function is that it obeys a second order differential equation, very much like this one. And that differential equation can be translated into a differential equation for the integrated correlator itself. And we call that as a Laplace difference equation, since it's an equation that relates the correlator for SUN theory with the correlator of SUN plus 1 and SUN minus 1. I should emphasize that this Laplace operator is SL to the invariant. So this equation is a SL to the invariant equation. So just as a comparison, the well-known non-holomorphic Einstein series obeys a, well, much simpler Laplace equation, takes this form. As I already said, since it's a kind of recursion relation, so once the initial data is given, say the integrated correlator for SU2 theory is given, then you can use this equation to determine all the correlators for arbitrary n, since we know the boundary condition from the perturbation. In the remaining few minutes, so I will just discuss a little bit this function in various limits. Let me begin by discussing the standard, say, perturbation expansion or loop expansion. So you can take the formula, just expand it in small coupling for arbitrary n. That is the expression you will find. So first of all, it looks simple, and then at L loop, basically you find the say zeta 2L plus 1 with some rational coefficient. As I already kind of discussed, one can take the known result of this correlation function and integrate it over the measure I gave it to you. And at least for the first 3 loops that we have checked, you will find this result. So setting in another way, the localization computation did match with the standard quantum field theory computation to the order we have checked. Another property you may notice is that the non-planar contribution indeed starts at the 4 loops. Again, that was also known from the more standard study. One may also look at the larger n expansion, so kind of genus expansion, and at each order of genus, one can expand in small lambda or large lambda. So let me begin with the small lambda expansion. Well, one can actually go pretty high, but anyways, yes, the concrete expression is not that important here. Just to mention one small thing, so we found that at each order, the theory is convergent with the same finite radius. Well, this property, I think, it has been seen in enforceable YAMLs for other physical quantities, such as the Casper's normal dimension or amplitudes. Now, one can also do a larger n expansion. As expected, now the expansion in 1 over lambda is half of the integer power. So one big difference is that the theory is asymptotic and not Boole-summable. Since we have concrete expression, so we can do a resurgent analysis and to complete it with non-perturbative terms. And that's the result we found. It takes this polylogical form. Maybe more relevant to us is another expansion, namely in the larger n expansion, but keep the YAML's coupling to be finite. So in this expansion, we find that only half integer power of a 1 over n appears, and the coefficient at each order is given by linear combination of the non-holomorphic Einstein series, which I introduced earlier. Compared to the finite n case, where the finite n, the correlator is given by sum over infinite number of non-holomorphic Einstein series. Another big difference is that the index, I probably didn't emphasize, there was an integer. Now it's a half integer. Okay. So as I promised, now I would discuss the other integrated correlator, namely you take the partition function and take a 4 derivative with respect to mass. This one turns out a bit harder to compute. So right now we don't have a expression for this integrated correlator at the finite n, but nevertheless, so in our early work, we computed this integrated correlator in the larger n expansion, but for finite coupling. And that's the expression we found up to order 1 over n to the q. So you notice that, besides half integer power n appears, we also now have an integer power n. And for the half integer power terms, the coefficient, again, is given by linear combination of non-holomorphic Einstein series. In fact, at each order, it's the same non-holomorphic Einstein series appear, but just with different coefficients. Now, for the integer guys, new modular invariance appear. We call it, well, it appeared early in the study was a string amplitude. This is called generalized non-holomorphic Einstein series. They are defined below. So maybe let me remind you, so in the case of a non-holomorphic Einstein series, they obey a very similar, say, Laplace equation, but it's homogeneous in the sense that on the right-hand side, it was 0 before. Now, so for this generalized guy, they have a source term, And this source term makes this equation actually rather harder to solve. And I think the solution to this equation for general, say R and S, is not known. So it was solved for this case. Say one big difference between this generalized non-holomorphic Einstein theory and the Einstein theory is that the generalized non-holomorphic Einstein theory receives contribution from both, say, instanton and anti-instanton pairs, but whereas for Einstein theory, just as instanton or anti-instanton just separate.
You have 5 minutes left, Congkao.
Okay, great. So in the final, say, 5 minutes, let me just discuss how one would reconstruct the original or unintegrated correlator. Well, the idea is rather simple. We just write the ansatz for the correlator. Well, to do that, it's most conveniently can be done in Mellin space. So let me just remind you. So say how the Mellin amplitude was defined. So you have a correlator, you do a Mellin transformation. So after you subtract, well, after you remove some gamma functions, what's remaining, often called the Mellin amplitude. Well, for good reason, one would remove those gamma functions, but let me not go into that. And Mellin amplitude was known to have a very similar property as a flat space amplitude. So therefore, we know quite well about its analytic structures. Knowing these analytic structures allow us to write, say, ansatz for the Mellin amplitude. So here C is the central charge, namely n squared minus 1 over 4. So I'm doing a larger n expansion for the Mellin amplitude. As I said, due to the fact that we know it's an analytic structure, so we were able to write the ansatz for it. Basically, the first term is the contribution coming from supergravity, and the second term is a contribution from r to the 4. Well, so because I factor out r to the 4, and this is the supergravity one loop. And then this term is a contribution coming from d4 r to the 4, and the last term I write here is coming from d6 r to the 4. As you notice, up to here, at each order of 1 over n expansion, there are mostly two unfixed say functions, and you can use these two integrated correlators to fix them. Indeed, so one can unambiguously fix this Mellin amplitude up to this order. At this moment, well, to fix, say, D6 out of the 4 on ADS5 cross S5, since we have, well, 3 unfixed coefficients, we need the 3 conditions. At this moment, we use the flat space limit, namely, by knowing the fact that if I take a flat space limit of the Mellin amplitude, I should reproduce the 10-dimensional superstring amplitudes. That gives me yet another condition combined with this 2 integrated correlator. I can fix all those D1, D2, D3. Done that, that's the answer we found for this say unintegrated correlator in the larger n expansion up to the order, say, D6 out of the 4. So say one consistent check is that one can take flat space limit of this Mellin amplitude, and we found that precisely reproduce known results of superstring amplitude in flat space. Of course, that check is not non-trivial for the D6 out of 4. As I said, I used flat space limit to fix this one. Okay. So just to avoid any confusion, so those coefficients is precisely correct, because when you do flat space limit, you have to do some integral going from ADS5 cross S5 to flat space, and those numbers are precisely correct once you do the integral. And yeah, okay. So let me just summarize and make some comments. So say, I guess the message I try to deliver here is that it is difficult to compute the correlator itself at the finite coupling, but maybe one can look for a simpler quantity. In my talk, I have been focusing on this integrated correlator. And we found that with the right choice of the measure, this became much simpler compared to the correlator itself, but yet it's highly non-trivial. So they can compute it exactly, but also provide useful tools for study non-perturbative effects. In my talk, I have been mostly focusing on this SL2Z property of enforceable amines. So in this talk, as I said, I have been mostly focused on one of the integrated correlator. And it will be interesting to generalize our results for the other integrated correlator at the finite end. So this correlator, this integrated correlator has been studied at the finite coupling in the larger n expansion order by order, at least to certain orders. It will be interesting to understand its structure at the finite end. It will be also interesting to say generalize the story for other correlators. I have been just focused on one correlator. Well, basically the simplest correlator in enforceable amines. One direction is that enforceable amines has this so-called bonus U1 symmetry introduced by interrogator. And for the correlator beyond the 4 points, it's possible to violate this so-called bonus U1 symmetry. And the mathematics associated with that is so-called non-holomorphic modular forms instead of non-holomorphic modular functions in the case of 4 point. So it will be interesting to study those objects even at the finite n. So in this paper, we studied the larger n expansion. As I already said, so this talk, I really just focus on the simplest 4-point correlation function of enforceable amines. It's a correlator of the lowest conformal dimension. It will be interesting to study, say, KK modes, correlated of higher weight, higher weight primary operators. So there has been interesting observation that those correlators, those KK correlators of KK modes are in fact kind of related to each other through so-called hidden 10-dimensional conformal symmetry. You may hear more from Coronado's talk. I think it will be interesting to study them in our content, say, understanding them at the finite coupling, at least for this integrated correlator. So anyway, thank you very much for your attention.
Thank you, Congkao. We got 2 raised hands. Let's start with Pedro.
Hi, thanks very much for a nice talk. I have a question. Can you summarize a bit what happens in ABJM? I already asked in the chat. My confusion is about the non-perturbative corrections. Do we have the same type of non-perturbative corrections at strong coupling? Because in flat space, those Eisenstein series analog, right, are much simpler. It's just the first few perturbative terms without the non-perturbative. Is there a counterpart for the gauge theory quantities, or only in flat space do they become simpler?
So in ABJM, it would be a map to say 11-dimensional M theory. The coefficient R to the 4 is much simpler. It would be just a number. There's no coupling dependence. So
I think I'm talking about the 't Hooft limit. So I think you are talking about your second limit, right?
Yeah.
So I was asking about your 't Hooft limit when you had this exponential of minus square root of lambda.
Oh, I see.
But maybe I should not be talking about that limit. I think that's the point.
I don't know.
I don't want to make it a discussion. I'll ask more in Slack.
Right.
Mukund?
Hi, thanks. I was curious if you could motivate physically why the particular measure was chosen for defining the integrated correlate. I didn't sort of probably missed it.
Right. Yeah. So, well, this was chosen basically because with that choice, it's related to the partition function of M2 star superamines. So the point that as I was saying, if you take a derivative with respect to the parameter, you bring down, say, 4 integrated operators. So these 4 integrated operators may or may not O2, the one I was interested in. So you have to do a super conformal transformation to bring them to O2. That was done in this paper. And so that will generate some factors. And furthermore, say it's on S4. I'm really interested in correlator on R4. So you have to do conformal map from S4 to R4 that generates some other factors. Combine all those factors together, as shown in those papers. That's the measure you will find. Yeah.
Thanks.
You.
It's perhaps related to the last question. You gave these two examples of integrated correlators. I mean, are there other potential integrated correlators which you could get nice results for, or are these somehow uniquely selected?
Right. So there's one more as we discussed in the literature. So I put it directly and to start super YAMLs on S4. One could put it on squashed S4. So there's a squashed parameter. Then one can do a derivative with respect to the squashed parameter, then we call B. So potentially, there's one more. Well, as far as I know, there's one more by taking two derivatives with respect to mass and the two derivatives with respect to the squashed parameter. However, we don't know if it's that's linearly independent. From localization side, in our paper, we actually we didn't prove, we provide the strong evidence from localization side, say two derivatives with respect to mass, two derivatives with respect to the squashed parameter is not linearly independent from these two. On the other hand, well, it's a possibility that as a measure, one may generate a linearly independent measure compared to these two. So that question is not settled, and just let me. Sorry, I'm sorry to change the slide. Let me just come to here. As I mentioned, to fix these 6 out of the 4, I need 3 conditions. Well, if I don't use the fast space limit, then we kind of feel there should be another one such that allows me at least to fix these 6 out of the 4. Since we kind of know the 6 out of 4 are BPS. It's a BPS.
So we should probably switch over to Anastasia now. So let's thank Congkao again. And Anastasia, can you share your slides, please? Great.